Hello and most welcome to 1099, the last shivering lecture before the 1100th. And I will today take up a rather complicated subject. What is reality, and is it even something to strive for? I will begin with an essay that I formerly started with by the professor Paavo Pylkkanen, who also was a friend of David Bohm, associated with him, and is currently active at the University of Helsinki, as well as the Department of Cognitive Neuroscience and Philosophy at the University in Skövde in Sweden. And the name of the article is The Quantum Epoché, borrowing its word from, of course, Edmund Husserl's epoché. And in this case, what are we going to put the epoché around? Seems that it is reality itself. I start at page 3. The first part is rather of a, what can I say, an introductory written and writing, and it will be quite enough to go into the meteor beat of the article, the essay. It is typical of later phenomenology, especially Heidegger, that there is much emphasis on the historical situation one finds oneself in, as well as on the situation and context in which meaningful phenomena unfold. This is another area where connections to quantum and relativistic phenomena seem relevant. Regarding his historicity, Heidegger emphasized that philosophy is a limited historical phase of Western thinking. As Backman describes it, philosophy in this Heideggerian sense is a metaphysical thinking aiming toward absolute generality that begins with Plato and Aristotle, but which has come to an end, especially as a result of the thought of Hegel, Marx, and Nietzsche. However, quantum and relativistic phenomena may give a new challenge and a possibility for renewal rather than end, even for philosophy in this traditional sense. And when it comes to situationality and contextuality, there are some interesting analogues to phenomenological themes, especially in some interpretations of quantum theory, as we will see below. There are thus a number of reasons why bringing together phenomenology and quantum relativistic physics is potentially fruitful. For one thing, this might enable new and more insightful phenomenological descriptions. Sorry about that. And when it comes to situationality and contextuality, there are some interesting analogues to phenomenological themes, especially in some interpretations of quantum theory, as we will see below. There are thus a number of reasons why bringing together phenomenology and quantum relativistic physics is potentially fruitful. I imagine. For one thing, this might enable new, more insightful phenomenological descriptions. As Bohm's above-mentioned discussion of time consciousness illustrates, also the methodological insights of phenomenology might prove useful when trying to make sense of the interpretational puzzles of quantum theory in particular. For example, we will below consider how a kind of epoché or suspension of assumption about reality at the quantum level seems to be required to make coherent sense of the results of some quantum mechanical experiments. Further, such bringing together of phenomenology and the new physics also seems to be in line with the very criteria for phenomenologists typically set to themselves. The empirical phenomena encountered in quantum and relativity physics have given rise to a new philosophical situation that poses a challenge to not only philosophy in a Heideggerian sense, but also to phenomenology broadly understood. Given the emphasis that later phenomenology puts upon historicity and situationality, it is somewhat ironical that there have been so few phenomenological discussions of the new epistemic and ontological situation opened up by quantum theory and relativity. However, this also implies the possibility for much fruitful research in the future. For example, there has been an extensive philosophical discussion of the meaning of quantum theory since the 1920s. Connecting this rich discussion with relevant aspects of phenomenological thought suggests a vast research program with possibilities of mutual criticism and enrichment between these two approaches. For examples of such attempts, see Honor 82, and especially in relation to post-phenomenology, Plotnitsky in 94, used to be my favorite book, to some extent it still is, Globus 2003, and Pylkkanen 1998. In this article, the theme of phenomenology and quantum physics is tackled by examining some basic interpretational issues in quantum physics. One key issue in quantum theory from the very beginning has been whether it's possible to provide a quantum ontology of particles in motion in the same way as in classical physics, or whether we are restricted to stay within a more limited view of quantum systems. in terms of complementary but mutually exclusive phenomena. In phenomenological terms, we could describe the situation by saying that according to the usual interpretation of quantum theory, especially that due to Niels Bohr, quantum phenomena require a kind of epoché, i.e. a suspension of assumption about reality at the quantum level. However, there are other interpretations, especially that due to David Bohm, that seem to re-establish the possibility of a mind-independent ontology at the quantum level. But as we will see, even such ontological interpretations contain novel non-classical features which require them to give a special role to phenomena or appearances, a role not encountered in classical physics. We will conclude that while ontological interpretations of quantum theory are indeed possible, quantum theory implies the need of a certain kind of epoché even for this type of interpretations. While different from the epoché connected to phenomenological description, the quantum epoché nevertheless points to a potentially interesting parallel between phenomenology and quantum philosophy. Our discussion also connects to some of the central issues discussed by Kaufman and Gar 2005 in the prologue to the special issue of GPVMB. For one thing, there is the question of measurement in quantum mechanics. Kaufman and Gar explore the possible role of mind in quantum measurements. They present a triad, a new view of quantum mechanics, which has actuals that are ontologically real and defined as obeying Aristotle's law of the excluded middle, possibles which are ontologically real and are defined as not obeying the law of the excluded middle, and mind, consciousness with qualia and free will doings at measurement. In short, res potentia and res extensa linked by mind at measurement. End of quote. Now, Bohm showed in 1952 that measurement-like processes at the quantum level can take place objectively without any active role of human consciousness. For a good introduction to how Bohm theory solves the measurement problem, see Ney 2013. In Bohm's quantum ontology, an electron is assumed to be a particle guided by a new type of quantum field, which latter is mathematically described by Schrödinger's wave function. In Kaufman and Gar's terms, Bohm showed that rest potential, understood as quantum potential, which arises from the quantum field, acts on res extensa, the localized particle aspect of an electron, in such a way that we get definite results of measurement without Schrödinger's cats or many worlds. Do here remember the frequency plane and the amplitude plane as shown by Stefan Mangold. That could be seen in one of the Kvantmöten. Those are, however, published in Swedish. All of this can happen objectively without the need for human observers of mind. According to the Bohm theory, measurement processes are a special case of quantum processes, such as transitions between stationary states, which latter take place in the nature completely independently of human intervention. This is some way similar to Kaufman and Gar's idea about some kind of proto-consciousness. Do remember that. Being present in quantum processes. There is also a connection to the issue of exophysics, which proposes a detached observer, and endophysics, which sees the observer and measurement as part of the domain that needs to be accounted for. First of all, there is a sense in which the Bohm theory allows us to retain an exophysical perspective to the universe. For if we assume that human observers have no significant influence upon the quantum state of the universe, then we can, for all practical purposes, ignore measurement and the active role of human observers in our general description of nature. Remembering, however, that Kantian considerations suggest that we probably have no perceptual or conceptual access to nature from a non-human perspective. However, there is also a sense in which the Bohm theory fits very well together with endophysics. For one thing, the Bohm theory provides perhaps the clearest available account of how the process of measurement can be accounted in terms of quantum theory itself, thus enabling a coherent endophysical discussion of quantum measurements. Bohm also sketched how the consciousness of the observer could be included into the picture. The basic idea is that the quantum ontology needs to be extended. At the quantum level, we have the particles guided by the quantum field of information. Bohm speculated that in the context of complex biological systems, such as brains, there is likely to be a whole hierarchy of such fields of information, ranging from manifest to more subtle and actively enfolding and unfolding information about each other, involving guidance relations. Mental processes and conscious experience could then come in at the more subtle levels of organization. Through the hierarchy of fields of information, mental processes and perhaps a kind of free will could make a difference to more manifest physical processes via the quantum field, suggesting another affinity to the ideas of Kaufman and Gar. Further, in his more general implicate order scheme, Bohm sketched how both biological and mental processes could be understood in relation to the physical world as described by quantum and relativity physics. The above considerations are meant to indicate that there are rich connections between Bohm and Heilig's natural philosophy to the general approach discussed in this special issue, especially as it is excellently brought out by Kaufman and Gar. In the rest of this article, we will, however, focus on the question about the role of phenomena or appearance in Bohr's and Bohm's interpretations of quantum theory. Now we get into next paragraph, which is called Niels Bohr's quantum epoché. Can we have an ontological description of quantum systems, say of particles such as electrons? In the domain of classical physics, it is possible to measure simultaneously the position and the momentum of a particle with arbitrarily good accuracy within a single phenomenon, and thus one is allowed to postulate a particle ontology. In other words, to make the transition from phenomena to ontology. Usually in classical physics, one just talks about the particle and its properties, ignoring the phenomenon in which these were measured. In phenomenological terms, this reminds me reminds us of natural attitude. We take for granted that objects that appear to us in experience also exist when not being observed. We slip from appearance to reality without noticing it. However, according to Niels Bohr, we cannot make a separation between the particle and the experimental arrangement in quantum situations, because the quantum action that connects them during a measurement is indivisible, unpredictable, and uncontrollable. For Bohr, this meant that we cannot analyze the quantum phenomena and assume that we are getting information about a separately existing particle with well-defined properties. In other words, there is no single phenomenon in which both the position and the momentum of a quantum system can be accurately measured at the same time. Thus, implied Bohr, it is not legitimate or meaningful to postulate an ontology in which a particle has simultaneously a well-defined position and momentum, as these supposedly exist irrespective of any act of observation. Nota bene, act of observation. We are doing something when we observe. One lecture ago I mentioned in 98 that there is always a posture, and we seem to forget that. Well, we all forget that. This is not part of knowledge, so to speak. It's not a question for knowledge, and I would say that it's the metaphysical ideas. This is what creates the metaphysical idea of a transcendent object. Thus, implied Bohr, it is not legitimate or meaningful to postulate an ontology in which a particle has simultaneously a well-defined position and momentum, as these supposedly exists irrespective of any act of observation. In phenomenological terms, we could say that Bohr was calling for a kind of epoché in the context of quantum phenomena, in the sense that suspend our classical habit of conceiving of a well-defined observation, a dependent ontology of particles in motion. So the issue for Bohr seems to be when it is legitimate to postulate an ontology, or to put it differently, what does the incompatibility of phenomena associated with a single system imply for the ontology of that system? The following quote captures many essential features of Bohr's subtle ideas. Quote, "This crucial point implies the impossibility of any sharp separation between the behavior of atomic objects and the interaction with the measuring instruments, which serve to define the conditions under which the phenomena appear. In fact, the individuality of typical quantum effects finds its proper expression in the circumstance that any attempt of subdividing the phenomena will demand change in the experimental arrangement, introducing new possibilities of interaction between objects and measuring instruments, which in principle cannot be controlled. Consequently, evidence obtained under different experimental conditions cannot be comprehended within a single picture, but must be regarded as complementary in the sense that only the totality of phenomena exhausts the possible information about the objects." End of quote. The phenomenological reader notices how the measuring instruments play a transcendental role for Bohr, as they define the very conditions under which the phenomena appear. A new kind of wholeness in physics is implied by the fact that no sharp separation between the behavior of atomic objects and the interaction with the measuring instruments can be made. This means that we typically cannot assume, when looking at the result of measurement in an experiment, that the result refers to the behavior of atomic objects as it unfolds independently of its being measured. This is in stark contrast to the situation in classical physics, where the theory allows us to calculate the influence of measuring instruments to a good approximation, and in this way get as accurate information about the behavior of objects as we want. Note also how Bohr says that it is because of such indivisibility or individuality that different experimental arrangements are mutually exclusive. If I want to measure the momentum of a particle in a situation where I am measuring its position, I need to make changes in the experimental arrangement. However, such changes introduce new possibilities of interaction between objects and measuring instruments, which, Bohr says, in principle cannot be controlled. This connects with the uncertainty principle and Bohr's assumption that the quantum of action needed in each measurement is uncontrollable. After the changes in the experimental arrangement required to measure the momentum of the particle, I can no longer measure its position. Thus, the experimental arrangements are mutually exclusive. Bohr further emphasized that we cannot comprehend the evidence from such mutually exclusive arrangements with a single picture, and yet we have different kinds of evidence about the same object. How should we consider such evidence concerning the same object? Evidence that is obtained from mutually exclusive, incompatible experimental phenomena. Do remember here Alice and Bob, very important. Bohr says that we must consider such evidence as complementary. Notice that complementary here cannot be understood in the sense of two parts of a single picture. Rather, we have here two incompatible pictures which, however, both give information about the object. Bohr says, only the totality of phenomena exhausts the possible information about the objects. That means, I say, observer and observed in totality. But this totality includes mutually exclusive phenomena. Very important. Bohr's notion of complementarity is thus very subtle, involving the necessity to combine incompatible viewpoints. Arkady Plotnitsky, in his 2010, provides a succinct summary of this difficult concept. Complementarity is defined by A mutual exclusivity of certain phenomena, entities or conceptions, and yet B, the possibility of applying each one of them separately at any given point, and C, the necessity of using all of them at different moments for a comprehensive account of the totality of phenomena that we must consider. As we have noted above, complementarity also implies that we cannot analyze the quantum phenomena and assume that we are getting information about the separately existing particles with well-defined properties. Note, however, that in recent years there has been an increasing interest in so-called weak measurements in quantum mechanics. While even these can be understood in the terms of Bohr's complementarity, they nevertheless open up the possibility for new ways of thinking about quantum measurement. Bohm and Heidegger describes the unanalyzable and holistic aspects of Bohr's view succinctly. Quote, "The quantum link connecting the experimental results with its meaning is indivisible, unpredictable, and uncontrollable. The meaning of such a result can therefore no longer be coherently described as referring unambiguously to the properties of a particle that exists independently of the rest of phenomena. Instead, this meaning has to be regarded as an inseparable feature of the entire phenomena itself. Or, to put it more succinctly, the form of the experimental conditions and the content, meaning of the experimental results, are a whole, not further analyzable. It is this whole that, according to Bohr, constitutes the quantum phenomena." Note that, according to Bohm and Heidegger, there is a relationship between form and content in a new special sense in Bohr's view. The form of the experimental conditions and the content or meaning of the experimental results are assumed to be an unanalyzable whole. This means that it is not possible to isolate a particle from this phenomenon and think about it in the traditional realist fashion. Bohr's holistic view implies limits to the visualization of atomic phenomena. For example, he thought that it is not possible to provide trajectories for quantum particles. He underlined that the renunciation of visualization of atomic phenomena is imposed upon us by the impossibility of their subdivision, and refer to the impossibility of subdividing quantum phenomena and the ambiguity in ascribing customary physical attributes to atomic objects. There is an essential ambiguity involved in reference to physical attributes of objects when dealing with phenomena where no sharp distinction can be made between the behavior of the objects themselves and their interaction with the measuring instruments." End of quote. Finally, Bohr did not think that the situation encountered with quantum phenomena was just a temporary state of affairs to be overcome in future developments. Following quote. "In quantum mechanics, we are not dealing with an arbitrary renunciation position. I need to make changes in the experimental arrangement. However, such changes introduces new possibility of interaction between objects and measuring instruments, which, Bohr says, in principle cannot be controlled. This connects with the uncertainty principle and Bohr's assumption that the quantum of action needed in each measurement is uncontrollable. After the changes in the experimental arrangement required to measure the momentum of the particle, I can no longer measure its position. Thus, the experimental arrangements are mutually exclusive. Bohr further emphasizes that we cannot comprehend the evidence from such mutually exclusive arrangements within a single picture, and yet we have different kinds of evidence about the same object. How should we consider such evidence concerning the same object? Evidence that is obtained from mutually exclusive, incompatible experimental phenomena. Bohr says that we must consider such evidence as complementary. Notice that complementary here cannot be understood in the sense of two parts of a single picture. Very important. Rather, we have here two incompatible pictures which, however, both give information about the object. I would say that needs to be so much emphasized. They are not two parts of a single picture. Never ever that. That can never ever happen. It's essential to understand that. Rather, we have here two incompatible pictures which, however, both give information about the object. Bohr says that only the totality of phenomena exhausts the possible information about the objects. But this totality includes mutually exclusive phenomena. Bohr's notion of complementarity is thus very subtle, involving the necessity to combine incompatible viewpoints. Arkady Plotnitsky, 2010, provides a succinct summary of this difficult concept. Complementarity is defined by a mutually exclusive. Sorry. I repeated myself here. I do beg your pardon. Finally, Bohr did not think that the situation encountered in quantum phenomena was just a temporary state of affairs to be overcome in future development. Quote, in quantum mechanics we are not dealing with an arbitrary renunciation of a more detailed analysis of atomic phenomena, but with the recognition that such an analysis is in principle excluded, end of quote. This is because we do not know the modus, the Stimmung, the posture, the attitude, how the subject is standing. Bohr's claim about the need for a renunciation of the visualization of atomic phenomena is interesting from a phenomenological point of view. Note in particular that the late Heidegger's post-metaphysical thought emphasized that the appearance of certain content is made possible only in relation to background context which itself does not appear. Thea alla fea. Somewhat Analogously, Bohr's complementarity implies that a given aspect, e.g. position, can fully appear only if we give up the attempt to make a complementary aspect, e.g. momentum, appear. In terms of David Bohm's later implicate order approach, which is in some way similar to Bohr's view, but differs in that it is more ontological and general, we could say that not every relevant property of a particle can be made explicate or manifest at the same time. Every quantum particle, and thus the entire universe, lives in an intrinsically implicate order, which can only unfold creativity to constitute the present moment. For example, if a given variable, e.g. position, is explicated in an experiment, the complementary variable momentum is left implicate and vice versa. Thus, Bohm's implicate order scheme, like the late Heidegger, emphasizes that for something to appear, there must be an entire implicate background, which cannot be made to appear at the same time. And Bohr assumed that it is not possible to go consistently beyond this phenomenologically limited situation by visualizing quantum systems with all their properties present simultaneously, as one does in classical physics. As we will see, it was Bohm who made such impossible visualization possible in his 1952 theory. Ironically, there is a sense in which Bohm's 1952 scheme, with its more explicate ontology, is in opposition to the more general implicate order scheme he developed since the 1960s. 3. Einstein, Bohm, and the search for a quantum ontology. For Albert Einstein, the programmatic aim of physics was a complete description of any individual real situation as it supposedly exists, irrespectively of any kind of observation. In other words, he felt that physics ought to strive for a kind of exophysical description that Bohr thought was in principle impossible. There was thus, as is well known, a fundamental disagreement between Bohr and Einstein about the interpretation of quantum theory. As we have already mentioned many times before, above, a very important contribution to this debate was made by David Bohm. After several interesting and stimulating discussions with Einstein in Princeton, Bohm published in 1952 an interpretation on quantum theory in terms of hidden variables. He realized that Schrödinger's equation implies a well-defined, visualizable, unambiguous ontology where an electron is a particle always accompanied and guided by a new type of quantum field, described by the wave function. He had independently rediscovered and improved the pilot wave theory proposed by de Broglie already in the 1920s. For an appraisal of de Broglie's contribution, see Baccia, Galuppi and Valentini from 2009. Bohm's theory was not, however, a return to classical physics. Although his 1952 theory was very deterministic, already in 1954, he published with Vigier a stochastic version of the theory, thus underlining that the key points of the theory was the possibility of a quantum ontology, not the issue of determinism. Stochastic means statistics or giving up determinism. Also, as Bohm and Heidegger brought up more clearly later, the Bohm theory was non-local and suggested the need for a new holistic description of quantum system. Now we already saw above that a certain kind of quantum wholeness was a key aspect of Niels Bohr's interpretation of quantum theory. So while there is a sense in which the Bohm theory differs from Bohr, e.g. in enabling us to analyze or break Bohr's indivisible quantum phenomena conceptually in terms of a particle guided by a quantum field, there are also important similarities. Bohm's interpretation was initially resisted, but is today more and more widely acknowledged as one of the key possible interpretations of quantum theory. Later on, further ontological models were proposed. For example, Everett's 1957 many worlds interpretation, Girardi, Rimini and Weber's 1986 objective collapse theory, and currently the nature of quantum reality as intensively debated within the philosophy of physics community. We do not know which ontological interpretation is correct, but each may reveal something significant about the nature of physical reality at a very fundamental level. One should note there are by now also different versions of Bohm theory. Much attention has in recent years been given to a minimalist version known as Bohmian mechanics. Bohm himself developed since the mid-1970s with Basil Hiley a philosophically more radical version they call the ontological interpretation, culminating in their 1993 book The Undivided Universe. We will here be concerned with Bohm's and Hiley's later development of Bohm theory. In particular, we will consider what the Bohm theory can offer in place of Bohr's quantum phenomena. The key point is that in Bohm's quantum ontology, too, the object and the apparatus participate irreducibly during a measurement. This means that the phenomena that reveals themselves in the apparatus, i.e. the results of measurement, typically cannot be referred to the object alone, but only to the totality of apparatus and object. This is actually very reminiscent of Bohr's view, but with the difference that we can now understand the way in which this peculiar, irreducible role of quantum phenomena is a result of holistic features of the quantum reality of particles and field. Bohm and Hiley also explain their philosophical position in some detail in The Undivided Universe. Although they are emphasizing the possibility of a consistent quantum ontology, it is clear that they are not advocating any simplistic form of scientific realism. For example, when they explain their general worldview and consider epistemic issues, they say, ultimately all of our thought, including theories, can be regarded as appearance, not to the senses but to the mind. Now, does that mean that theories in the end have to do with the way the world appears to be rather than the world is? This sounds like a concession to Bohr's approach that emphasizes that we cannot go beyond phenomena when dealing with atomic objects. Traditionally, ontology refers to the way the world is. A brief etymological detour gives us some useful terminology. According to one interpretation, the word ontology comes from the Greek logos perita onda, where ta onda means the beings. Logos has the meaning like word, speech, reason, and peri means around. Perhaps in this context, about. So ontology originally would have meant something like reasoning about the beings. So in these terms, are Bohm and highly reasoning about the beings or about the way the beings appear? Or do they suggest that everything in the end is in the end appearance? There is thus at least prima facie creative tension between the claim that their theory gives us an ontology and that the claim that theories constitute appearances. As already mentioned, this tension is particularly interesting when considering the relation of the view to that of Bohr. One might think that the whole point of an ontological interpretation of quantum theory is to try to go beyond Bohr's quantum phenomena. Indeed, this is what Bohm and Hailey set out to do. But as we will see in the end of the quantum ontology, suggests that the relation between appearance and the underlying reality or essence in the quantum situation is radically different from that in classical physics. Their view has some striking similarities to Bohr's view, while there are significant differences as well. Now we go into paragraph 4. Bohm and Hailey on appearance and essence. To understand Bohm and Hailey, hereafter B&H, views about appearance and essence in the quantum domain, as described in the undivided universe, it is useful to first consider their view about scientific theories in general. They propose that there is no final theory. This implies limitations to what we can say about the universe as a whole on the basis of a scientific theory. For example, we cannot decide on the basis of a particular theory, such as quantum theory, whether the universe is ultimately deterministic or indeterministic. And thus we cannot use physical theories to draw conclusions about, say, the ultimate limits of human freedom. Their view here resembles that of Kant, who held that physical theories only apply to the phenomenal world, while the thing in itself remains unknown. Thus, any determinism that physical theories may involve does not limit human freedom insofar as this is grounded beyond the phenomenal world. Colin Marshall, 2012, described Kant's view succinctly. Kant holds that much of reality remains unknowable, yet he takes this to be a desirable result, for it precludes scientific considerations which only concern the appearance-based properties of objects from ever ruling out freedom of will. End of quote. Although BH emphasis on ontology may suggest to some that they are engaged with pre-Kantian Aristotelian metaphysics, we will see that the issue is more complex than that. Indeed, BH emphasis on the limits of theories resembles in some ways Kant's view that the Ding an sich is unknowable. However, we will see below that BH assumes in a realist fashion that there is a sense in which limited domains of mind-independent reality can be known. In this sense, they differ from Kant and connect with critical scientific realism. Their focus on ontology also connects them with the ontological concerns of Heidegger and Merleau-Ponty. It is clear from the above that BH do not expect that physics will lead to a theory of everything. Rather, they propose that nature in its total reality is unlimited, not merely quantitatively, but also qualitatively in its depth and subtlety of laws and processes. End of quote. Indeed, Bohm put forward such a notion of qualitative infinity of nature already in his 1957 book, Causality and Chance in Modern Physics. BH then note that if nature is qualitatively infinite in the way suggested above, it makes it possible that what we at any given time consider reality may always turn out to be mere appearance in relation to some more fundamental essence, which scientific research may discover. However, such discoveries may require speculative new concepts which go far beyond what can be observed at the time of their proposal. This emphasis on the value of concepts about the currently unobservable domain again connects BH strongly with the realist tradition in the philosophy of science. A key role that concepts about currently unobservable domains or levels can have is that they help us to detect evidence which otherwise might not be recognized at all. For example, the atomic hypothesis, going back to Democritus, made people alert to the kind of large-scale evidence that could support the existence of atoms. By making use of such evidence, the initially unobserved atoms had become part of the observable domain. BH emphasized that deeper explanations often imply the limited validity of what were previously the basic concepts, while the latter are recovered only as approximations or limiting cases. They point out that this relationship of concepts prevails not merely in physics, but is typical of the whole of our experience. As an example, they consider what takes place as we go round a circular table. Quote, "What we see immediately is an ever-changing elliptical shape. We have learned to regard this changing shape as mere appearance. The essence, i.e. the true being, is considered to be a rigid circular object." End of quote. Do remember here, I had to put in, Gibson do not agree. Gibson do not agree with this. Modern neurology wouldn't agree either, at least some strains. However, further investigation shows that the table is an atomic structure. The rigid circular object is now considered as appearance, while the essence is a set of constituting atoms. Yet deeper studies show that even the atom is an appearance, while the essence is a nucleus surrounded by electrons. And even these nucleonic particles were seen to be appearances, while the essence was a set of yet more fundamental particles such as quarks, gluons, preons, or else sets of excitations of string. The ontological lesson is that matter is turning more and more into empty space with an ever more tenuous structure of moving elements. End of quote. This is even more so in quantum field theory, which treats particles as quantized states of a field that extend over the whole space. BH then draw attention to the fact that in its historical development, something has been constant. There is a pattern in which at each stage certain features are regarded as appearance, while other features are regarded as one of essence, which explains the appearance on a qualitatively different basis. What is taken as essence at any stage is later seen to be appearance of still more fundamental essence. This means that ultimately everything plays both the role of appearance and that of essence. BH suggests that this pattern never comes to an end. They take this to imply that, that ultimately all of our thought, including our theories, can be regarded as appearance not to the senses but to the mind. They add what science is aiming for is that these appearances be correct. Correctness here means that the actions flowing from them, such as experiment, be coherent with what the appearances would imply. Incorrect appearances are thus either mistaken or illusory. They illustrate this idea with the example of the table. To have the appearance of an elliptical object is correct only in a very limited sense. If we bring in the thought that the object is a rigid circle, we obtain a more nearly correct overall set of appearances. While the thought of the atomic structure makes the whole set still more nearly correct, and so on. The example illustrates how we are constantly extending the appearances with the aid of thought. The ultimate reality is unlimited and unknown. It is somewhat like Kant's Das Ding an sich. However, its successive appearances serve as an ever more accurate guide to coherent action in relation to this reality. One might wonder how this compares with the idea of approaching the final truth. BH emphasizes in a somewhat phenomenological vein that our theories are not primarily forms of knowledge about the world, but rather they are forms of insight that arise in our attempts to obtain a perception of a deeper nature of reality as a whole. They add that we should not expect the development of theories ever to come to an end, any more than we would look forward to a final sense perception. 5. Ontology versus appearance. We have seen above that BH suggests that even our basic concepts and categories of thought are ultimately appearances. This also applies to the basic concept of their own ontological interpretation. So we might ask, are they doing quantum ontology or quantum phenomenology? Are they reasoning about the beings or about the way the beings appear? Specifically, we could ask, if physics essentially involves reasoning about the way the beings appear, what is the point of making an ontological interpretation of quantum theory? This is roughly the question I put to David Bohm in London in the spring of 1991, in the course of the many philosophical discussions I had with him while working on my PhD thesis. The Undivided Universe was then a manuscript, and I read and commented the draft of chapter 14.2. As far as I can remember, Bohm's reply to this question was added to the manuscript and can be found in pages 324 to 5 of the book. It seemed to me that Bohm's strong focus on appearances and theories as perception leaned toward an empiricist, pragmatist, and anti-ontological or anti-realist interpretation of science, rather than realist or ontological. This, of course, seemed to be in contradiction with the very name of BH interpretation, ontological interpretation, that is, included in the subtitle of their book. In their answer to this type of criticism, BH pointed out that every theory is not only a mere appearance. It is more. Its basic concepts must be said in some sense to reflect reality within its own domain. How does this differ from other ontological theories? Why, in other ontological theories in physics, it is either implied or asserted that such basic concepts correspond to independently existing realities. For example, not dependent on the context or deeper levels of being. In BH approach, the basic concepts of a given theory may reflect a reality that is inherently dependent either on context or on a deeper levels or on both. BH thus emphasized that ontology is reasoning about dependent beings, not reasoning about substances in the sense of ontological independence. Their view constitutes a kind of monism. There is only one independent being, the unlimited and unknowable totality. To understand this better, let us follow them in reconsidering the example of the table. In what sense are the elliptical appearances of a circular object realities? Consider the light coming from the object to the eye, how the eye makes an elliptical image carried into the brain. This is an essential part of the reality corresponding to the elliptical appearance. This reality is not independently existent. It depends on a context including the above process, especially on the circular object, which is the essential meaning of the elliptical appearances. But even the circular object is found to be dependent for its existence on a wide range of contextual parameters, e.g. temperature and especially the atomic constituents, etc., as we go through a series of deeper essences and appearances. Let's go to 6. Appearance and essence in the quantum domain. What about the quantum domain? Remember our question. Are BH reasoning about the beings or about the way beings appear? How would they answer this question in the quantum domain? They say interestingly that in the quantum domain it is no longer possible, even in the ontological approach, to move from appearance to essence in the way we have described above. Why not? They emphasize that the beings in a typical quantum experiment participate irreducibly in each other. This means that it's not possible to locate, individuate the essence that is supposed to underlie a given appearance. Considering measuring the momentum of a particle in classical physics, the appearances show themselves in the measuring instrument. The essence can be thought of as the property, momentum possessed by the particle. The measuring instrument then typically reveals the momentum that the particle had before the measurement. There is, of course, always a disturbance involved, but this can be accounted for in principle without limit. However, it does not work like this in the quantum domain, where the observed system and the measuring instrument participate irreducibly in each other, like in the Alice and Bob experiment or example. BH emphasized that the appearance, measured value, cannot typically be traced into an underlying essence, state of the observed system before measurement. Indeed, we have to consider appearance and essence, that is system plus apparatus, as a totality. The appearance show themselves as large-scale results that are observable in the apparatus, while the essence is the whole quantum ontology of quantum fields and particles, including those of the apparatus and the observed system. The observed momentum typically reflects the state in which the observed system was left after the measurement process is over. In this sense, the observed momentum reflects the whole experimental context, and it seems that undivided wholeness is lurking behind the appearances at the quantum level. This is very reminiscent of Bohr's indivisible quantum phenomenon, but we can now understand how this indivisibility is a result of the underlying holistic quantum ontology. Now into 7. Does Bohm and Heidegger's ontological interpretation constitute a form of scientific realism? Well, let us summarize Bohm and Heidegger's view about the appearance and essence. They say that each form of thought of the essence is an appearance, which however also reflects a reality. They emphasize that this reality is always dependent for its existence as well as for its qualities and properties on broader context and deeper levels. This is one of the senses in which the theory is ontological, in spite of the fact that all thought gives appearance. Also, BH approach provides a reflection of reality that is in the form of a totality, including the measuring instruments along with everything else. This implies that BH approach is a kind of endophysics in this, that it is not possible to eliminate the effect of the measuring apparatus in, say, momentum measurements. Well, is a BH approach realism? Note that in their theory, observations of position really disclose position. The idea of measurement as being able to disclose pre-existing properties seems to be characteristics of realism in the traditional sense. But this is not the case for momentum, as we have emphasized. Typically, the momentum that is measured is created in the act of measurement, which means that pre-existing momentum values are not disclosed by the act of momentum measurement. As Arthur Fine 1996 has emphasized, with respect to all other variables than position, the ontological interpretation is not realist in such traditional sense. We have also seen how BH emphasized that the reality that our theories can reflect is always a dependent reality. They assume that the reality that science is dealing with at any stage is inherently dependent either on context, e.g. temperature, or on deeper levels, atomic structure, or both. At the quantum level, there is the special feature that the object and observing apparatus participate irreducibly in each other. This dependence has major philosophical implications for them. So, does BH interpretation constitute a form of scientific realism? We have seen that it is realism in the sense that the independent reality of the universe is assumed, as well as the possibility to perceive the deeper nature of reality as a whole without theories. However, many features of traditional realism are denied. Theories are primary forms of insight, perceptions, appearances to mind. They are not primarily forms of knowledge about the world. Truth is not primarily correspondence between theory and reality, even if a correct theory reflects reality with its own domain. An important aim of science is to develop correct theories, appearances to the mind. Correctness is evaluated not in terms of correspondence between propositions and states of affairs, but in terms of pragmatic criteria. For according to BH, correctness of theory requires that the actions flowing from it, such as experiments, be coherent with what the theory implies. And the assumption that reality is infinite and unknown implies that science cannot reach a final theory of everything. Paraphrasing Kant, Arthur Fine has suggested that reality with this disclosure is blind. BH assumed that we can never disclose the whole of the ultimate reality. because it is unlimited and unknown. Is such a BH-style reality without disclosure blind? One thing to note here is that no absolute limits to disclosure are assumed. So the veil is always in principle removable. Also, when BH quantum ontology is situated in the broader implicate order framework, with the introduction of higher levels of organization, the way is open to an understanding creativity and biological evolution in a new way. Concluding reflections. We started off by considering the relationship between phenomenology and the revolutionary philosophical implications of quantum and relativity physics. We then noted how Niels Bohr's interpretation of quantum theory implies the need for a certain kind of epoché, or suspension of assumption about reality at the quantum level. We further saw how, even in the context of Bohm and Heidegger's ontological interpretation of quantum theory, it is not straightforward to adopt the natural attitude toward the empirical phenomena. For example, a momentum measurement cannot be understood as a revelation of pre-existing, well-defined property of the observed system. Thus, even the Bohm-Heidegger interpretation implies the need for a kind of epoché. We have to suspend our natural classical tendency to assume that from the observable large-scale results of measurement, we can infer pre-existing state of the observed system. It is not clear how literally we should take the analogy between Husserl's epoché and the varieties of quantum epoché we have briefly sketched above. In the Husserl case, an important aim of the epoché, or bracketing, is to enable the unbiased study of conscious experience. In Bohr's case, suspending assumptions of reality at the quantum level is a crucial part of this subtle notion of complementarity, which captures the mutual exclusivity of certain experimental quantum phenomena. In Bohm and Heidegger's case, the need to suspend the move from appearance to essence in the context of, say, momentum measurements is a result of the radically participatory nature of quantum ontology. While not denying that these cases are different, it seems fair to say that in all of them, the epoché serves the achievement of a clearer and more truthful picture of the domain under interest. I would like to add to this that the observing object can also be seen as understanding or experience. And in some way, it all boils down to experience, not even words or relationships, but something pre-verbal. So everything has to be measured in this so-called matter or substance I call experience. And this is the one part, and the other part is the exophysics, if this is the endophysics. So I would see that experience itself is what modulates together with the endophysics modulating also the exophysics also modulating the endophysics. And what I'm trying to put in my hand is, of course, the Klein bottle, showing that subject is part of the object and object is part of the subject. And boiling down to experience itself, I think something that is important here is cause and effect. Because by arbitrarily point to something in the exophysics and calling that particular thing cause and effect, put a limit also on understanding or experience. And I would say this limitation, this narrowing, is what causes this apparent absolute division between subject and object. At the moment, I'm sorry, I can't make it clearer than that, but I had a sort of epiphany here, I would say. I say thank you very much. It was a great pleasure having you today, and I wish you a very pleasant afternoon. Bye bye for now.